Oh man, 35 points. This sucks. All right, this one right here. What is that point right there? That's -3. -3 positive 2. So I'm going to take dy over dx, and I'm going to plug in -3 positive 2, and this is what it looks like: -2 over -3. Now, because one of these numbers is negative, I know that it's going to become a positive. And that's it. Look, it's 2 over 3. 2 over 3 is my slope. So you got to think, that's a rise of 2, a run of 3. It's just below 1. Now, a slope of 1 would be a perfect diagonal, kind of like that, because up 1, right 1, right? Okay, so it's just less than that, so I'm just going to kind of, I mean, it doesn't even matter if it looks exactly like 1, but that is the slope right there. And then you got to do it again for this one. I know, right? And so let's get rid of this 2 right here and put a 1. And no more 2, got a 1. Oh, so now it's 1/3. So now I got to do a positive slope, but a little less steep. And so it kind of looks like it, but maybe not as much. I mean, there's not that much of a change, so you're not going to get dinged for something like that. All right, now the next one, this point right here, that is 3, 0. So we're not doing 1 anymore, we're doing 0. So now this is a 0. Oh, hey, 0 divided by 3, that's 0. That's the easiest slope to draw. That's a horizontal line. So I'm going to do a horizontal line just like that. And you have to do this for every single point for this slope field. That's the tediousness. That's how long it would take. And, I mean, the point is not that you finish this. The point is that you get this, and that makes sense to you. But you do it until it makes sense. Does this make sense?
Yeah.
Okay, and then recognize things. Like when you hop over to this side right here, you're doing positive numbers. And so your slope's actually going to be negative. Your slope actually for all these points right here should be negative, shouldn't it? Actually, not for these ones, because those would have a slope of 0 because of the y. If you have a y on top that is 0, then all those are going to be 0. In fact, yeah, since I can think, I'm going to just do that. I'm like, hey, these are all 0. Okay, but you know what? I have to be careful when they're both zeros, because what does this equal? -0 divided by 0. Does that equal 0? No. That's nothing. That is an undefined slope. You cannot divide by 0, even if you have a 0. If you divide 0 by 0, it's still undefined. In fact, let's think about that for a second. If the x is 0, it's always going to be undefined. And so all the points that have an x that is 0, I'm just going to put a vertical line right there. Those would be undefined. Does that make sense to you guys? And so, like, I'm already kind of shortening it. I'm noticing a couple of patterns, but that's how it's going to look. All of these points right here should be a positive point. All these points right here, let's see, that's a negative number and a negative number. Wouldn't those be negative? Yeah, so those will all be negative. And then these would all be, those will all be positive. And then these right here would all be negative. So negative slopes, positive slopes. And you should see some variation and some kind of a change from one point to the next point. It doesn't have to be perfect, just kind of perfect. All right, so let's plug that guy into our slope field generator. Boom. So look, it looks like, yep, every point in this quadrant is negative, and this one is all negative, and these ones are all positive, and these ones are all positive. And so it looks like our prediction on like what our baby tangent lines look like is correct. But let's go back to the differential equation and find a general solution for it. All right, so what we're going to do here is we're going to do something called separating the variables. And so when we separate the variables, what you're doing is you're trying to get all the y's on one side and all the x's on the other side. So the equation just has two variables, and if it has that, you can separate them. So I'm going to do what looks like multiplying both sides by dx. That cancels out the dx's, and so then I'm left with dy equals negative y times 1 over x dx. Now, I hope that's okay with you guys. Does that make sense, me splitting this up? I put the y down here, or right in front, so we can more easily get rid of the y, or see how we would do that. see if we actually put a 1 underneath it, we would just multiply straight across and we get right back to where we were. But if I separate it, it makes it kind of easier to see, I think. So what I'm going to do to get that y over to the other side is I'm going to multiply both sides by negative 1 over y. And I could keep the negative over here, but I'm going to go ahead and throw the negative over there with that guy. And so it would look something like this. Negative 1 over y times dy equals 1 over x dx. And then what your job is next is to integrate both sides. So we're going to go ahead and integrate both sides. I'm going to put the negative on the outside because he's pretty much like a scalar. Right? And then after I do that, let's do our integration. We have the natural log of y and take the absolute value of that. And I'm not going to put plus c, even though I should, because this is that indefinite integral. There's not an upper and a lower bound. And on the other side, I'll have the same thing. And on this side, I'm actually going to put the plus c. We only need the plus c on one side. We don't need to have the plus c on both sides. If you did have the plus c on both sides, I mean, think about that. If we subtract c from this side to this side, and we don't know what c is, you can't go c minus c. It's more like c sub 1 minus c sub 2. C sub 2 will be over here. You're just going to get another c, so you just get another arbitrary constant. And let's not forget our negative that goes out in front of that. All right, so you didn't finish finding the general solution until you get the y value alone. Okay, so that's what we're going to do. We're going to get that y value alone because we're going to write a function in terms of x. I'm going to take this negative 1 and I'm going to put it as an exponent on the y on the inside. So actually that's going to be 1 over y. And then to get the y out of the natural log, I'm going to raise each side to the base of e. Now you're raising the whole side to the base of e, so that means the whole side becomes an exponent. And so we have the e and the natural log canceling out, and so you're left with y to the negative 1, which I'm going to write as y, or 1 over y. On the other side, we have e to the natural log of the absolute value of x plus c. And I'm going to do a little bit more manipulation here. I don't want to have the y on the denominator. And so, I mean, what you could do is you can cross multiply and then divide and all this stuff. But essentially what's going to happen is the other side is going to be on the bottom of a fraction, and the y will not be on the bottom of a fraction anymore. So we would have y equals 1 over e to the natural log of x plus c. Now I'm going to do a little bit more simplifying. If you guys remember your exponential laws, they would say something like this. If you had, let's say, a raised to the x times y, that is the same, or not times, I'm sorry, plus, x plus y. That's the same as saying a to the x times a to the y. And what do you do with these exponents when you multiply common bases? You add them. And that's what's happening right here. We have exponents that are adding to each other. So I'm going to rewrite that to say e to the natural log of x, and then times e to the c. Now, this e is going to cancel out with that natural log, and so we're going to have 1 over x times e to the c. But the more official way to write that, not official, but this is just the more common way to write that. You'd put the e to the c and then multiply it by x. No, actually, I think I do like that, the way that it's written right here. You just probably wouldn't write that dot. All right, so that's our function right there. Let's graph that on our slope field to see if it matches the slope field, the differential equation. Oh, and this is a general solution because we still have the c. We don't have the point that we could plug in to find the value of c. All right, once I throw that into my Desmos slope field calculator, because I want to see if it matches up, it's asking for what I want to put in for c. I'm going to go ahead and say make c into a slider, so then it gives it a value. So right now the c's value is 1. What happens when I change that 1? It looks like we still follow every single baby tangent line. So this, my red line right here is a particular solution currently, but if I change the c, we can see all the different particular solutions that we can get that would fit this slope field. And now that I'm looking at it, it looks like I probably should have left the absolute value bars around the x. That's probably more correct. And the reason is because if I if that x was negative, that would flip my particular solution to fit the other tangent, baby tangent lines. So yes, my answer should have an absolute value bar around the x. So that is the general solution to this differential equation.